All right, so this is for the second FRQ. So for this FRQ, we've got these two pulleys, and both pulleys are being pulled by these like spring scales. It's basically something to measure force, and they're pulled down with the same amount of force, right? So there's the same amount of force acting on both. Both of these pulleys have the same mass and the same radius, but pulley A is just a solid disk, and pulley B has almost all its mass concentrated out at the rim. So they're being pulled at the same force. We're supposed to predict which pulley will complete one revolution first. So we need to think about which of these pulleys is going to have more acceleration. So first off, for both of these pulleys, right, both of them have the same amount of torque because they both have the same amount of force pulling down, right, equal to Fs. And they both have the same radius value. So for both of these pulleys, the net torque is the same. So if we want to compare them, well, whichever one has a higher angular acceleration, right, that's the one that will complete a revolution first. And whichever one has less rotational inertia will have higher angular acceleration, right? So less I means more alpha, and more alpha means it will complete one rev first. So we need to identify which of these has a greater rotational inertia. Well, they both have the same mass, and you probably recall that the rotational inertia for a rigid object with shape is I equals some number times m r squared. And the m is the mass of the object, the r is the radius. Both of these are the same. So we need to just think about that fraction out in front, which one of them is greater. Well, that beta value, whatever that fraction is, I like to use beta, not everybody does that. The one with the mass concentrated further towards the outside will have a higher number there. And that would be this one, right? Because this is sort of like a hollow cylinder. Right, all the mass is at the edge, and here there's mass kind of spread out between the center and the edge. So this one's going to have less rotational inertia, and it will therefore have more angular acceleration and complete one revolution before that one does. So the answer here is pulley A. All right, derive an equation for the time it takes pulley A to complete one revolution. And they're giving us the rotational inertia, and then they're asking us what to put our answers in terms of. Again, physical constants, that's stuff like G. So here, it's pretty clear that we're going to have to, again, sort of use Newton's second law for rotations. I say again because it's like the other FRQ. We're probably also going to have to use some kinematics. So the net torque in this situation, it's pretty straightforward. It's just R times that Fs, that scale force. That's the net torque on the disk, and this should be equal to I alpha. They're both in, let's say, the positive direction. And the I is actually IA. So if we solve for, well, we can't really solve for anything yet, but we need an equation for the time. So now let's think about what kinematic stuff we know. Right? We know the initial angular velocity is 0. We know the angular displacement for one revolution should be 2 pi. We know the... Do we know anything else? We are looking for the alpha, but we don't know it. We don't know the final angular velocity, and we don't know it. And, wait, are we looking for the alpha? No, we're looking for the time. Don't know the time either. But what we could do is, we kind of do know the alpha because we could use our work here from this equation to give it to us. So we should be able to build an equation that has alpha and TA, and then sort of smoosh that into this equation to get rid of the alpha. So let's go ahead and give that a try. We can kind of tell that since that final angular velocity is the thing that we don't know and we don't care about, we want to use the equation with no final angular velocity, which is this equation, delta theta equals omega naught t plus 1/2 alpha t squared. This is 0, and the t is actually TA in this question. And delta theta is going to be, we actually know that too. It's 2 pi. And let's just go ahead and maybe, let's solve for alpha. So if we solve for alpha, we get 4 pi over TA squared is equal to alpha. Yep. And now we can take that and we can plug it in here, and then we can solve for our TA. So if we plug that in for alpha, we get RFS equals IA times 4 pi over TA squared. And then if we solve for our TA squared, we get TA squared equals 4 pi IA over RFS. And then TA is equal to 4 pi IA over RFS square rooted. Got a little messy there at the end. Okay, let's just keep going a little bit. Is our answer for part B1 consistent with part A? Well, yes it is, because we can see that the rotational inertia and the time have a direct relationship, right? More rotational inertia means it will take longer to do that one rotation. So yes, and I kind of gave you the reasoning. Okay, for the next part, we are attaching a block, and the block is released from rest. Describe how the net torque exerted on the pulley and the magnitude of the angular momentum of the net. We're not worried about angular momentum, but the net torque, it's not changing, right, while the block is released. Because if we think about it, this thing will have a constant acceleration, and the tension force will be constant, right? And if the tension force is constant, then the net torque on the pulley will be constant. Okay, and now this last part. So for this one, similar, but now we've got this wrapped around, and as it unwinds, notice that the radius where the string actually touches actually changes. So we're supposed to predict how the net torque, and we're not worried about energy, right? We haven't talked about that yet. But as the scale moves down, the radius actually is going to change, right? So the net torque is basically R times tension, but the radius decreases, which means the tension, which means the net torque is actually going to decrease. All right, I hope this was helpful.